we're going to look at problem number, let's just say 16. P minus 4 squared equals 49. So when we go about solving this one here, we are going to use the square root method because we do only have one variable. It's inside the set of parentheses being squared. Now the first thing we want to do is get it by itself. So if there's anything added or subtracted to it, if something we had plus 5, we're going to subtract 5 from both sides. If it's minus 7 from both sides, we're going to add 7. We need to get the set of parentheses by itself. Now, since there is no number added or subtracted, we don't have to do that there. If there's a number being multiplied in front of the parentheses, we would have to divide it, get it by itself. But luckily for us here, the set of parentheses is already by itself, which means we can take the square root of both sides. Yes? On the left-hand side, the square root and square would cancel, leaving us with p minus 4 is equal to plus or minus. Well, the square root of 49 is 7. So once we take the square root of both sides, we find that p minus 4 is equal to plus or minus 7. At this point here, we can solve for the variable. We can solve for the value p. And to do that, we would add 4 to both sides, because our negative 4 plus 4 would be 0, leaving us with p. And whenever we add or subtract this number, we're always going to put it in front of the plus or minus. So we're going to have positive 4 plus or minus 7. Yes? We good with this here so far? Are 4 and 7 like terms? So we could definitely say that p is equal to 4 plus 7. We can also say p is equal to 4 minus 7, yes? Well, what is 4 plus 7? 11. 4 minus 7 is negative 3. Yeah, no, there's a reason I went back over this, because if we can add or subtract, we need to add or subtract. Because we got like terms 4 plus or minus 7, we can do 4 plus 7, we can do 4 minus 7, we get to solutions. Now, if it was, say, 4 plus or minus 7 square roots of 2, we're done. Because 4 and 7 square roots of 2 are not like terms. For us to be able to add or subtract these, we would have to change 7 square roots of 2 into a decimal. We'd have to approximate it because it's an irrational number, and then add or subtract those. And we would only get approximations. We would not get the exact answer. So 7 square roots of 2, we would leave it as this here. But because it did simplify completely, we can add, we can subtract. If we can combine them, we need to combine them. If we can't, we leave it. Does that make sense? I did want to hit that before we started today, just so that we can see if we can combine them, we need to. All right. We're going to start today's lesson. So this was up on the board when y'all came in. We want to find a number when multiplied by itself get you a negative number. Did anybody come up with a number for this here? We're trying to find a number when multiplied by itself gives us a negative. Well, what could we try? Well, just pick something. We can multiply 0 by itself, and 0 times 0 is 0. Unfortunately, 0 is not positive or negative, so we really didn't get what we wanted. Let's say 1, because if we multiply 1 by itself, well, 1 times 1 is 1. That's not a negative number, so what could we say? Negative 1 times negative 1 is 1. So whenever we multiply a number by itself, we're always going to get a positive number. Because really what we want to say is we want to have some number when multiplied by itself gives us negative. Well, we'll just say negative 1 because that's going to be the simplest form of this here. At this point, we're going to have to imagine some number when multiplied by itself is negative 1. So we're going to call this imaginary number I. So when I is multiplied by itself, we get negative 1. But this doesn't work. There is no number, no real number when multiplied by itself that gives us this negative 1. It's not real. It's an imaginary number. But this also means if I took the square root of both sides, square root of I squared is I. And for this here, we're not really concerned with the plus or minus. I is, by definition, the square root of negative 1. We have to have this because being able to take any radical or solve any of these quadratics, these higher degree polynomial functions where we're having to find a square root of a negative number, trying to find what times itself is negative 1, we have to have this I term. So we have set by definition I is equal to or is defined to be the square root of negative 1. But we also have that I squared is just negative 1. But that means these radicals here, these square roots, which up to this point we've not been able to find or get or have values for, we can actually find the value of now. Because if we look at A, the square root of negative 25, we can really break this up into two numbers. Because we can say that the square root of negative 25 is really, we're taking the square root of negative 1 times 25. According to our properties of radicals, if I have two things multiplied inside the radical, I can break them apart into 2. Because our square root of A times B is equal to the square root of A times the square root of B. And we can actually find out what this is. Now, the square root of 25, what times itself is 25? 5. The square root of 25 is just 5. Because the square root of negative 1 up to this point is what we did not have. We did not have a way to find this. There is no way to find this. But the square root of negative 1, we have said, is what? Square root of negative 1 is I. So the square root of negative 25 is 5i. Because we had to imagine, we had to create this number when multiplied by itself as negative 1. Which, especially as we started talking about this a few minutes ago, it seemed like, why would this help? Well, now I have ways to find this here, find values for this. So we know that the square root of negative 25 is 5i. Let's look at B. We have the square root of negative 72. Now we can do like we just did. We can break this up or look at it as negative 1 times 72, which we can say is the square root of negative 1 times the square root of 72. So negative 72 here. So yes, it is, because negative 1 times 72 is still negative 72. We split it apart to break it apart because when we do negative 1 times 72, we can say it's the square root of negative 1 times the square root of 72. Our square root of negative 1 is going to become I. Now we can actually find the square root of 72. Is there a number times itself that gives us 72? No. So if we're doing this by hand, we have to look for perfect squares, numbers that multiply by themselves as factors of 72. There's different ways to go about it. We can do factor trees. We can see what perfect squares are divisible by 72. If I look at 72, the first perfect square that we have, because we have 4, 9, 16, and then it is 49. 72 divided by 4. 18. So 36. Or, what did we also say? The 30xs, this yellow calculator is great with square roots, yes? Try typing into the yellow calculator the square root of 72. It is 6 square roots of 2. The reason this works is because 72 is 2 times 36. Here. Square root of 36 is 6. So we can't simplify our square root of 2. And what did we say the square root of negative 1 is? Is I. So the square root of negative 72 is 6i square roots of 2. Now we could try plugging the whole thing into the 30xs, saying second square root negative 72, it gives us a domain error because it cannot find the square root of an imaginary number. Most likely y'all are set here. If we plug it into the graphing calculator, square root of negative 72, there's a good chance it's going to give you this here. Non-real answers. Because yes, we already said square root of negative 72 is not a real number. It is an imaginary number. So what we can do, and I'd turn your graphing calculator on, is up at the top there should be a button that says mode. There's a button on that calculator that says mode, M-O-D-E, up at the top. And it should bring up this list here. And as you look down that list, you should see something that says A plus BI. A plus BI. Go down to it, select it, and hit enter. Now you'll know it's been turned on if it goes from black text to white text in a black box. Anything that's white text in a black box is turned on, it is active, it is working. So that tells us now that we do have it in A plus BI mode. Once we have it in that mode, we can go second quit, we can come back to it. It will take the square roots of negative numbers. So down, all right. So scroll down. Yep, keep going down. Because it might have gone, yeah, let's see here. There we go. Yep. Once you get it set to that, you go second quit. Now you can type in negatives inside of radicals. But if you notice this here, for this one, it gives us 8.485821374i. Because as we saw already, square root of 72 is not a perfect square, so we get 7 square roots of 2. Questions on this here? So what we've seen so far is, one, the graphing calculator can do it as long as the number inside the radical is a perfect square. It can take it just as it is. We don't have to change anything. which means the first one, square root of negative 25, it will indeed tell us that it's 5i. Yes? But if it's not a radical or a perfect square, it does not give it to us. Like with B, it did not directly tell us that it's 6i squared roots of 2. It calculated 6 square roots of 2 as a decimal approximation, and we had our I term. Questions on this here? We kind of see what's going on between the two calculators, yes? Mm-hmm. Yes. Second, quit, second mode.
So I'm at the second mode.
So, yep, second mode one more time. Yep. Yeah, because it goes back to the home screen, so whatever you typed in or had typed in. So now you can plug in the square root of negative 72, and it'll do it, and it'll work. Now, let's look at C, negative 5 square root of negative 9. Negative 5 square root of negative 9. So we still have the negative 5. Now the square root of negative 9, well, we can do the same thing we've been doing. We can say that the square root of negative 9 is the same as the square root of negative 1 times 9, which is indeed the same as the negative 5 times the square root of negative 1 times the square root of 9. However, we know that the square root of 9 is 3. And the square root of negative 1 is I. Because by definition, square root of negative 1 is I. Square root of 9, 3 times 3 is 9, so it's going to be 3. So that tells us that the square root of negative 9 is 3i. So what we have at this point is we have negative 5 times 3i. Well, what's negative 5 times 3? That's just negative 15, yes? So negative 5 times 3i would be negative 15. And that's our final answer. Now, since this is a nice number, it means that if we wanted to, we could take the graphing calculator and say negative 5 second square root negative 9. It actually tells us it's negative 15i. Questions on this here? Square root of negative 4. So 30xs won't do this because it's a negative. Is 4 a perfect square? Well, yes. What times itself is 4? 2. And the negative, what do we know about the negative inside the radical? It's going to come out as what? It's our negative 1, yes? And what is the square root of negative 1? I. So we know that negative is going to have to come out of the radical as I. It's our negative 1. It's that multiplication of negative 1. So we know it's going to come out as I. So really, at that point, all we've got to focus on is the square root of 4. Because the negative is going to come out as I. Square root of 4 is 2, telling us that the square root of negative 4 is 2i. Now, this can be helpful, because especially if we look at 2, square root of negative 12. The one of the two, the 30x s, will not take the square root of negative 12 because it's an imaginary number. The graphing calculator will not simplify the square root of negative 12. But we know that this negative is going to do what? It's going to come out as I, yes? So really, what are we looking at now? We're just looking at the square root of 12, yes? Well, the 30xs be able to simplify the square root of 12 in radical form? No. Because 12 is 4 times 3. Square root of 4 is 2. Telling us that this is really just 2 square roots of 3. Which means the square root of negative 12 will be 2i square roots of 3. We're starting to be able to see here how these simplify. Number 3, we have negative square root of negative 36. That one negative, the negative outside the radical, it's still there because it's not a part of the radical. We know that the negative inside the radical is going to become what? I. And what's the only thing we have left in that radical is the 36, yes? What's the square root of 36? 6. Which tells us that negative square root of negative 36 is going to be negative 6i. Questions on this here? 2 square root of negative 54. We still have the 2, and it's being multiplied with the square root of negative 54. Now, the square root of negative 54 is not a perfect square. But we know whatever it is, whatever it reduces to will have I, because that negative is going to come out as I. Now, if we work through the factors and work through this here, we can try to see, are there factors or perfect square factors at 54? And that would be 6 times 9. Square root of 9 is 3. 6 would stay inside. Square root of 54. 3 squared to 6, because our 9 would simplify to 3. Telling us that the square root of negative 54 is 3i square roots of 6. And lastly, we can multiply. 2 times 3i. 2 times 3 is 6. You got it. So the square root, or 2 times the square root of negative 54 is 6i square roots of 6. Questions on this here? Questions on anything we've done so far? Now, we are not finishing this packet today. I will tell you that right now. But at this point here, I think we feel comfortable with simplifying radicals with negative numbers inside of a radical. Yes? Now, I think since I is equal to the square root of negative 1, it does some interesting things. The fact that this works, and it works as nicely as it does, I think is kind of interesting. Powers of i's also have something interesting that takes place. Because so far what we've said is I is, by definition, the square root of negative 1. That's just the definition of I. And the way we got there is we said I squared because we were looking at a number times itself to be negative 1. So I'm going to take this a step further. Let's look at I to the third power. We're going to multiply it by itself 3 times. So really, we can say that we have I squared times I. We could have also said that it's I times I times I by itself 3 times. I'm going to use I squared times I, because that is still I to the third. But we know what I squared is. I squared is negative 1. We found that, we stated that already. So we're just multiplying it by another I. And negative 1 times I is negative I. All right. We're going to multiply it to the fourth power. We're going to do it again. So this is I multiplied by itself 4 times, but we're going to use a nice fact about the fact that I do know what I to the third is. We already found I to the third. We simplified it, so we're going to use it, because really I to the fourth is just I to the third times I. And as we found already, I to the third power is negative I. So really for I to the fourth, we can consider it the same as negative I times I. Well, I times I, anything times itself, is I squared. And it would be negative because we have negative I times I. Well, we know what I squared is, yes? I squared is negative 1. So really we have negative negative 1, which is 1. Okay? Now at this point here, nothing really kind of insightful has happened yet, at least that we can see. Okay? Well, since we've gone to the fourth, might as well continue on to the fifth power. And we'll follow this same pattern. We'll say that I to the fifth is the same as I to the fourth times I. Well, what did we say I to the fourth power was? 1. So really this is the same as 1 times I, or just I. Questions on this so far? I'm going to keep going. I to the sixth power. Well, that'd be the same as I to the fifth times I, yes? What did we say I to the fifth is? I. So we really just have I times I. Which is the same as I squared, which is just negative 1. Anybody have a guess at what I to the seventh is going to be? Negative I. It's going to be negative I. Because I to the sixth times I to the sixth is negative 1. Negative 1 times I is negative I. Now, if we look at I to the eighth, it's 1. Because I to the seventh times I, which is negative I times I squared, negative. We can keep doing this pattern, but what do we notice? We go I, negative 1, negative I, 1. I, negative I, negative 1, negative I, 1. And really we can just move the top one over a little bit, because that's just square root of negative 1. So we said I to the fifth is I to the sixth, I to the seventh, I to the eighth. And it's just repeating this here. Because no matter what the power of I is, it's going to reduce to one of 4 things. I, negative 1, negative I, or 1. And this is actually really neat or really interesting, because if we think of any other number, any other term, besides 0 and 1, because 1 just tells us it's 1 all the way through, 0 to any power other than 0, just 0. This here we have this oscillation between these four here. And we get this property when we evaluate powers of I. We divide the exponent, whatever the exponent is, by 4, and we're going to get one of these four things here. So whenever we take I to the n, we're going to take the power of n and divide it by 4. If the decimal is 0.00, it's going to reduce to 1. If the decimal is 0.25, it's going to reduce to I. If the decimal is 0.50, it's going to be -1. And if the decimal is 0.75, it's going to be -I. So really, for finding powers of I or evaluating this, we can take whatever the exponent is and divide it by 4 and match it up. So if we looked at evaluating I to the 27th, all we've got to do is take the 27 and divide it by 4. 27 divided by 4, 6.75. So we said 0.25 was I, 0.50, 0.5 was -1, 0.75 is -I, and 0.00, most calculators aren't going to show a decimal, is 1. Now since the decimal here is 0.75, we don't care about the 6. This reduces to -I. Because the reason we're ignoring the 6, we're not focused on the 6, because if you notice when we were doing the powers of I, we went through one cycle by the time we got to 5. So we went one through full cycle, and then we went a quarter of a cycle, so that's 1.25. Here it says we went through those 4 terms 6 times, and then 3/4 of the way around to get to -I. So I to the 27th is -I. If we look at I to the 34th power, if we want to simplify this, we do what? We take 34 and divide it by 4. 34 divided by 4 is 8.5. It's -1. Yes. So there's 4 main terms. So the reason we're dividing by 4 is there's 4 options that we can have for I. It's either going to be I, -1, -I, or 1. So as the powers increase, we're going to be in one of these 4 spots. So the nice thing with this is that depending on which of the 4 it is, the decimal will tell us which one we're at. So if we're at 0.25, it tells us that we're at I. We have I to the first power. 0.50 tells us that we would get down to I squared. 0.75 would be -I, and 0.00 means that we have full groups. We're really breaking the power up into groups of 4. So really what we're saying with 34 is that I can say that I have 8 groups of 4. Because 8 times 4 is 32, so I to the 32nd would be 1 times I squared, the 2 I left over. Because when we multiply like bases, we add the exponents. So this is going to be 1, and I squared gives us -1. Does that make sense? Let's look at number 6. We have 47 over 4. So we're going to divide 47 by 4, and it'll tell us how many whole groups we have, which is 11. But the main part that we care about is the decimal. So it's telling us we're going 3/4. We have I to the third left over. And I to the third is negative I. Fractions on this here. I to the 65th. Second decimal on the graphing calculator. Second decimal gets us what? I, yes? And we're looking at I to the 65th. It tells us it is I, because 65 divided by 4 is 16.25. 0.25 responds to I. So it tells us that this is I. All right. I think the last one is I to the 1040, yes? 1040 is divisible by 4, so it gives us 0.00, which would be 1, yes? And this here tells us it is 1 plus 4e negative 12i. Now, I would not write that whole thing out. 4e, I'm going to write it here, 12i. Now, what the calculator is saying with 4e negative 12i, e in the calculator is understood to be 10. Because really what it's saying is 4 times 10 to the negative 12th I is what the calculator is saying. That's scientific notation. Now, times 10 to the negative 12th, that means we're moving the decimal 12 spots to the left. So, really what we have is 1 plus, we have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's really what that number is. And for us here, for all case in point, that number might as well be 0. So it's really just telling us that this is 1. The way the graphing calculator calculates this out and works it out, it's not dividing by 4. It's actually using graphing notation and graphing parts of the imaginary number I to get this here. And once we start getting bigger and bigger numbers, it has a pixel of graphing error that starts showing up. That's what this is. So that 4 times 10 to the negative 12th is essentially almost the size of a pixel. Pixel error. So really just 1.
May I have your attention, please? There will be an SBA meeting today during lunch in Coach Coffee's lab room. Thank you.
So the graphing calculator with finding powers of I works well up to a certain point. Then we have to know that the number time, or whatever the number they give us, e to the negative 12, e to the negative 14, that part is just 0. Then we take the other part, either be 1 or negative 1, or I or negative I. Or we can just divide that power by 4 and see which one it lines up with. Here and there. We'll stop here. We'll do this possibly tomorrow. We'll see.